Hello all. In my previous lecture, I discussed case 2, that is VGS is constant and when VDS is varying. And also I discussed relation between I and voltage, right? Means IV relation in a MOSFET. Okay. Now in this lecture, what is the IDS equation in linear region and saturation region, right? So first I will start with IDS in linear region. IDS in linear region, right? See, tell me, what is the condition for linear region in case of N channel? When MOSFET is in linear region, MOSFET in linear region, what is the condition here? The condition is here, MOSFET is in linear region when, what is the condition? When VDS is less than VGS minus VDH, right? Then you know what happened? What is the current equation actually? IDS is equal to mu n into COX W by L VGS minus VTH into VDS minus VDS square by 2. Actually, this is the current equation for a MOSFET, right? See, in case of linear region, VDS is less than VGS minus VTH, means I think the square of the VDS is a very small value, so that we can neglect this term actually. Therefore, okay, here this IDS equation is nothing but what? This IDS in IDS equal to mu n into COX W by L VGS minus VTH into VDS, right? That means here we are neglecting VDS. See, for example, if the VDS is 0.1, for example, what is the VDS square? 0.0. It is a very small value, right? So we can neglect it. So here, this is the current equation in which region actually? Linear region. This is the current equation in linear region. Yeah, from this, I can also define a channel resistance. Channel resistance. That is denoted with RDS. What is channel resistance? Channel resistance is nothing but it is the ratio of VDS by IDS. Yeah, from this equation, what is the VDS by IDS actually? VDS by IDS is nothing but what it is? This is simply L by mu n into COX W VGS minus VDH. Okay. See here, this is the channel resistance. So in case of channel resistance here, when VGS is varies, what about the channel resistance also varies? Channel resistance also varies actually. Here, that's why this MOSFET is called as actually voltage dependent resistor, voltage variable resistor. See, when you are varying the VGS, the channel resistance also varies, right? So we can say voltage dependent resistor or voltage variable resistor in case of linear region, right? Write down. Yeah, next heading, put the heading IDS in linear region. Case 1, IDS in linear region. Yeah, write down. MOSFET is in linear region. MOSFET is in linear region when VDS less than VGS minus VTH. VDS less than VGS minus VTH. Okay. Therefore, write down the current equations actually. Here, write down here. This VDS is small in case of linear region. So we neglect it. Write down. Also write down the channel resistance. Yeah, when VGS is varies, right on. When VGS is varies, channel resistance also varies. Channel resistance also varies. Hence, MOSFET acts as a hence MOSFET acts as a voltage variable resistor or voltage dependent resistor. Voltage variable resistor or voltage dependent resistor. Right. Yeah, this is about ideas in linear region actually. Next heading, ideas in saturation region. Ideas in saturation region. Ideas in saturation region. Right. So no. So tell me, what is the condition for saturation? MOSFET is in saturation. When? What is the condition? MOSFET is in saturation. When VDS is greater than or equal to, right? VDS is greater than or equal to, consider VDS is equal to VGS minus VTH, right? Then what is the current equation here? Then IDS is equal to mu n into COX W by L VGS minus VTH VGS minus VTH VGS minus VTH whole square by 2. Just in place of VDS, substitute VGS minus VTH. Okay. Now what is this equation here? Then current equation IDS is equal to mu n into COX W by L. This simply VGS minus VTH whole square by 2. Yeah. This is the current equation in case of saturation region. Right. Now let us consider this mu n into COX by WL is nothing but kn dash. Or you can also define one more parameter actually, mu n into W by 2L. W by 2L. This is nothing but kn. You know what is this kn and kn dash actually? Simply transconductance parameters or transconductance parameter. Transconductance parameter. Now what is the current equation in this case? IDS is equal to, this is simply Kn, this is simply Kn into VGS minus VTH whole square. Yeah. Very important equation. Current equation saturation. Okay. Yeah. Copy. Right on. Yeah. Next heading. calculation of transconductance GM. Calculation of transconductance GM. Calculation of transconductance GM. Yeah. See here. First of all, what is transconductance? Transconductance is nothing but it is the ratio of change in drain to source current to the change in gate to source voltage. Means simply we can say output current by input voltage. Okay. How to calculate this transconductance? Differentiate this equation here in saturation actually. What is the differentiation actually? Dou IDS by dou VGS is equal to Kn into what is the differentiation of VGS minus VTH whole square? Simply it is 2 into VGS minus VTH. Okay. Now what is this? This is nothing but GM actually. Now 2Kn into VGS minus VTH. Right. Now what we can understand from this equation? So here clearly the transconductance is proportional to what actually VGS minus VTH. Now what we can understand here? So here the transconductance is linearly increases with VGS. From this equation we can say that the transconductance is linearly increases with VGS. Okay. So linearly increases means see the graph actually transconductance versus VGS graph. Conductance versus VGS graphs here it is linearly increases. Okay. See here this is theoretically, but practically this is not linear here. Practically it is not linear. See why practically it is not linear. See what happened. I think this will be oxide, this will be gate, and this will be channel, right? This is VGS. Yeah. See here, you know practically what happened? After reaching the maximum value, transconductance, it start decreasing. This is practically. Theoretically, it is simply linear. Right? Why practically after reaching the maximum value, it will start decreasing? Because, see here, because due to decreasing of mobility of the charge carrier, due to decreasing of mobility of the charge carrier nothing but electrons. Okay, here why this why mobility of the charge carrier is decreases? Because of strong attractive force offered by a oxide layer. See, when VGS is increases, you know what happened? When VGS is increases actually, you know what happened? This oxide layer offers an attractive force. Because of this attractive force actually, okay, the charge carriers will not reach us to drain. So what happened? The conductivity starts decreasing. That means practically after reaching this maximum value, this transconductance start decreasing due to decreasing of mobility of the charge carrier. Due to decreasing of mobility of the charge carrier, this mobility of the charge carrier is decreased due to what? Due to strong attractive force offered by a oxide layer because of increasing of VGS. This is happening in case of practical, right? Yeah, copy here. Next, calculation of transconductance. Yeah, copy up to here. Yeah, right on. Therefore, the transconductance is linearly increases with VGS. Transconductance is linearly increases with VGS. In bracket, theoretically. In bracket, theoretically. Yeah, next, write down note. 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 Practically, After reaching maximum value, the transconductance starts decreasing. The transconductance starts decreasing due to decreasing of mobility of charge carrier. Decreasing of mobility of charge carrier in bracket electrons. In bracket electrons. Means here, why electrons means in channel electrons are the right majority charge. That's why. If you consider p channel, then it is holes. But here I am considering n channel, so that's why I am telling in brackets electrons. Okay. Next one. The mobility of the charge carrier is decreased. The mobility of the charge carrier is decreases due to attractive force offered by a oxide layer. Due to attractive force offered by a oxide layer. Yeah. Copy the diagrams. Transconductance versus VGS graph. Very, very, very important here. See, theoretically linear, but practically it is not linear. Huh? Yeah. See, this is the transconductance in terms of what? VGS. Right? Yeah, now I want the transconductance in terms of IDS here. Then what we will do? What is the value of VGS minus VDS from this equation? Just under root Kn, right? Under root IDS by Kn, right? Now what is the GM here? So here this is the GM in terms of VGS, right? I want GM in terms of IDS. Now GM into 2Kn. Yeah. What is the value of VGS minus VTH? Under root IDS by Kn simply. IDS by Kn actually. Here the Kn and Kn cancel. Now GM equal to what? GM equal to 2 into GM equal to 2 into here under root Kn into IDS. Kn into IDS. Now see this equation. From this equation, what is the conclusion? Here the transconductance is sublinearly increases with IDS. See, transconductance is linearly increases with VGS, but it is sublinearly increases with IDS. Now what is the graph? Transconductance versus current IDS graph? GM and IDS. See, this is sublinear. Yeah, this is the transconductance in terms of IDS. Copy. Yeah. Next. Copy na? Yeah. Next topic. Channel length modulation. Channel length modulation. Copy parallelly. Copy now. Yeah, next topic, channel length modulation. Yeah, what is channel length modulation? See, when VDS is made to very high, then what happens? See, the depth of the channel at the drain end almost zero. See, for example, when VDS is made to very high and increases further, means for example, if you increase the VDS beyond the high value, then what happened? You know what happened? The pinch off point is moving away from the drain. The pinch off point is moving away from the drain, due to which the channel length is decreases. Due to which the channel length is decreases. Here the channel length is decreases because of what actually? Due to increasing of the VDS, right? Yeah, this is called as channel length modulation. Like in BJT base width modulation, in FET there is an effect that is channel length modulation. You know, this channel length modulation is negligible in case of long channel length MOSFETs. It should be considerable in case of small channel length FETs. Getting or not? See, in case of long channel, there is no problem of channel length modulation, but in case of short channel, okay, there is a problem of channel length modulation, right? Write down please. When VDS is made to very high, and increases further, when VDS is made to very high and increases further, then the channel length is when the VDS is made to very high and increases further, then the pinch off point is moving away from the drain. The pinch off point is moving away from the drain, due to which channel length is decreases. Due to which channel length is decreases. Channel length is decreases. Channel length is decreases. Next, this decreasing of channel length due to increasing of VDS is called as channel length modulation. Right. Next point. See, it is negligible. It means channel length modulation. It is negligible in case of long channel length MOSFETs. It should be considerable. In case of short channel length MOSFETs. Right. See, all of you. What happens when channel length is decreases? See here. See, when VDS is increases, what is the channel length here? Channel length is decreases, right? Channel length is decreases. If channel length is decreases, what is W by L actually? Increases. If W by L is increases, means whatever the current IDS increases. See, do you observe or not one thing here? If you see the characteristics, means output characteristics of MOSFET, that is IDS versus VDS, okay, in saturation region, the current IDS is independent of the VDS. Actually, this is the saturation region, right? So here the current IDS is independent of the VDS. See here, independent of the VDS. See, when VDS is changes, whatever the current actually here, constant, that means independent. But because of channel length modulation, the current IDS is depends on what? VDS. The current IDS is depends on VDS. Okay? Yeah. Here, current IDS is depends on VDS. Then what is the effective current IDS with considering channel length modulation? Right? That we will have to calculate. Yeah, first write down this point here. Write down this flow graph. Write down this flow graph. Completed? Yeah. Next, put the heading. Calculation of ideas. Calculation of ideas with channel length modulation. With channel length modulation. Calculation of ideas with channel length modulation. Right. See here. Calculation of ideas with channel length modulation. Now tell me, because of channel length modulation, what happened to channel length? Decreases, right? Then what is the current equation? You know, the current equation ideas is equal to mu n into COX W by L dash, Ln dash into VGS minus VTH whole square by 2. VGS minus VTH whole square by 2, right? Yeah, what is Ln dash in terms of L actually? L minus delta L. Ln minus delta L. VGS minus VTH whole square by 2. Whole square by 2. Now what is IDS here? IDS is nothing but mu n into COX W, common the Ln here, 1 minus delta L by L whole square. Sorry here. VGS minus VTH whole square by 2. Okay. Now tell me, what is this equation here? What is this equation? I think this is the equation IDS in which region? Saturation. That is IDS of sat. That means simply we can say without channel length modulation, right? Now what is IDS here? IDS is equal to IDS of sat by 1 minus delta L by Ln. You know, I think 1 by 1 minus x is nothing but 1 plus x square, so on. Here I am neglecting higher order terms actually. Simply it can be written as IDS of sat into 1 plus delta L by Ln. Delta L by Ln. Okay. Now here, see, in case of channel length modulation, the delta L is proportional to delta VDS. Means the change in VDS, if you change the VDS, so length also proportionally changes, means increases, right? The change in delta L increases. That means we can say delta L is proportional to delta VDS. See, VDS increases, length decreases, but this delta L will be increased. Delta L is increased. That means we can say delta L is proportional to delta VDS. Here we avoid this proportionality, we can put a lambda dash. Delta L is equal to lambda dash into delta VDS. Okay. Now multiply both sides on Ln actually, this one. Then delta L by Ln is equal to lambda dash by Ln into delta VDS. Okay. Now let lambda dash by delta n can be replaced with lambda. Then delta L by Ln is equal to lambda into delta VDS. Right. Now what is the current equation here? Substitute this lambda into delta L by Ln, right? Lambda into delta VDS. Then what is the current equation? IDS is equal to IDS of sat into 1 plus lambda into delta VDS. Yeah, this is the current equation with channel length modulation. With channel length modulation. For example, if channel length modulation is negligible, That means we can consider lambda is 0. Then what is the current IDS value? IDS equal to IDS of SAT. Right? Yeah. Copy. Yeah. Copy now? Yeah, write down. When lambda is 0, lambda is 0 in bracket, lambda 0 means channel length modulation is negligible. Channel length modulation is negligible. Negligible. Then IDS is equal to IDS of SAT. IDS is equal to IDS of SAT. Yeah. Now I can also define units of lambda here. You know what is the units of lambda? See from this equation, see all of you, what are the units of delta L by Ln? Unitless ratio, na? See delta L meter, Ln also meter, so unitless. Then what is the units here? So lambda is equal to, what is the units actually? Volt inverse. What is lambda here? This lambda is nothing but modulation coefficient. Modulation coefficient. Yeah, right on. Units of lambda. Units of lambda is volt inverse, where lambda is modulation coefficient. Modulation coefficient. Modulation coefficient. Right. See, what about the output characteristics with channel length modulation? See, without channel length modulation, this is an output characteristics, right? So with channel length modulation, the output characteristics like this. This is simply minus 1 by lambda comma 0. Like, do you remember? In case of BJT, we have early effect. Due to early effect, actually the output characteristics are extended towards negative. Like in case of FET also, okay, due to channel length modulation, the output characteristics are extended towards negative side. That is simply it is minus 1 by lambda comma 0. You know, sometimes they are giving early voltage in problems. You know, early voltage V early is nothing but simply it is 1 by lambda. V early voltage is nothing but simply 1 by lambda in problems. Okay, copy our output characteristics. Yeah. Next heading, calculation of output resistance R naught. Calculation of output resistance R naught. Calculation of output resistance R naught or RDS. R naught or RDS. Yeah, first I will define output resistance. First I will define the output resistance. Okay. Output resistance is nothing but it is the reciprocal of slope of output characteristics of MOSFET, right? Yeah, what is the slope of this curve actually? See, for calculation of the slope, assume this point is VDS 1 comma IDS 1, right? Now what is the slope here? Y2 minus Y1 by X2 minus X1. That is simply, I think it is IDS 1 minus 0 by, see how to calculate actually. How to calculate? See, a small correction here. We will calculate from this formula also. We can consider like that also, but from this we will get easily here. So what is we are saying slope of the output characteristics of the MOSFET, right? What is the slope actually for this curve? Slope is nothing but dou IDS by dou VDS, right? Huh? Slope is nothing but dou IDS by dou VDS actually. Dou, it can be written as dou VDS by dou IDS. Yeah, this is nothing but output resistance. Yeah, how to calculate this one actually? Just differentiate this equation here. Differentiate this equation actually with respect to VDS. Then it is dou IDS by dou VDS is equal to then IDS of SAT into, but the differentiation of this one actually, differentiation of this one is nothing but lambda, right? Differentiation of this one is lambda. Now tell me what is R naught here? R naught is nothing but what is R naught? So R naught is nothing but simply it is 1 by lambda into IDS. Same you are getting here. If you calculate like y2 minus y1, x2 minus x1, you are getting same. R naught is equal to 1 by 1 minus 1 by lambda into IDS. This is the output resistance. Okay. See, when channel length modulation is negligible, then what is the output resistance here? Infinite. Means lambda will be 0, then R naught is infinite. Very, very, very important expression. Copy. Write down. Output resistance is nothing but is equal to, copy. It is a reciprocal of slope of output characteristics of MOSFET. Yeah, from this also you can calculate. Not only, see, if you differentiate this equation you will get the same. From this also you can calculate how it will calculate actually. I think this also I will show it. Simply slope is nothing but y2 minus y1, right? So that is IDS minus 0. This is simply x2 minus x1, right? Okay. This is simply VDS minus of minus plus 1 by lambda, right? Actually this VDS is very, very small value compared to early voltage. This is early voltage, right? 1 by lambda is nothing but early voltage. It is a very, very small value. So we can neglect this VDS. Then what it is? IDS into lambda. Slope. This is nothing but a slope, right? Now substitute this slope in this, then simply it is 1 by lambda into IDS. You'll get the same. Yeah. Write down a question here. One problem. Write down. A MOSFET in saturation region. Write down a question. A MOSFET in saturation region has a drain current of 1 milliampere for VDS is equal to 0.5 volts. VDS equal to 0.5 volts. If the channel length modulation coefficient is 0.05 volt inverse, 0.05 volt inverse, the output resistance in kilo ohms of the MOSFET is, output resistance in kilo ohms of the MOSFET is. Yeah. All of you read the question here once. What is given data? They given a drain current. How much in saturation? That is IDS of SAT. Actually, this is IDS of SAT. Right? What is IDS of SAT? They given actually 1 milliampere, right? Also, they given lambda modulation coefficient 0.05 volt inverse. All right. Well, here we want to calculate R naught, right? Output resistance. Then what is the formula? 1 by lambda into IDS of SAT, right? What is lambda here? 0.05 into IDS of SAT. IDS of SAT is nothing but 1 milliampere. So which is equal to how much? Just it is 20 kilo ohms. 20 kilo ohms. Yeah, copy. Yeah, thank you. We will continue in next lecture.